Hi, I'm Carl, and in this video we're going to go over questions 81 to 84 of section 3 of the pink booklet. So this is a question about colour. So we're told here that most organic compounds appear white or colourless, and some are coloured because they have groups that absorb some parts of the visible light spectrum. And so they go on to explain what these groups are. So we're told that aromatic rings can absorb some of the visible radiation, but also conjugated double bonds. And I want to go over quickly what a conjugated double bond is. So we're told here that multiple bonds separated by single bonds are said to be conjugated. So say you've got double bonds like this, then a single bond, then a double bond, and then that just sort of continues. And these are called conjugated bonds. But we're told that it's not only in this sort of linear fashion. Say we've got a line of carbon atoms like this, and we've got an oxygen atom here, or a nitrogen here. These are called multiple bonds because obviously there's multiple of them, and so they would be considered conjugate bonds as well. Right, with all that aside, let's have a look at question 81, which provides a lot of information, not much of which is useful, but it does give us this equation, which I've copied out here, and this is the molar absorptivity equation. So the question says, what would the molar absorptivity of a compound if at the wavelength at which the maximum absorption occurs, 90% of the light passing through a cell of a width of 2 centimeters containing 0.05 molar solution of this compound is absorbed? So there's quite a lot of information there, but thankfully it gives us everything we need to do this question. So we can just start off by plugging the numbers in. So we're told that at the wavelength at which the maximum absorption occurs, 90% of the light passing through the cell. So A is going to be the proportion of the light absorbed. So 90% would correspond to 0.9 proportion. And then if we're looking at the other two, we were given concentration as 0.05 and the width or the path length of 2. So then that gives us 0.9 over 0.1, which simplifies to 9, and then we're given the units there as well, which are going to be moles per centimeter cubed. Great, so that gives us an answer B for 81. 82 says many synthetic dyes are based on azobenzene, and it gives us this diagram here, which I'll just copy out quickly. So you can see it's got these, I didn't draw that very well. You see it's got these sort of aromatic groups here, and we've also got another conjugated bond here with these nitrogens. There's only 2, okay. And then we've got another aromatic ring like this. And so if we were to add another group to this, what would we want to add so as not to increase the wavelength at which the maximum absorption occurs? So really we've been given 4 different groups here, and the question is which of them isn't conjugated, because that would increase the wavelength at which the maximum absorption occurs. So looking at a carboxylic acid, you'll know that it will have this structure here, got this multiple bond here, and so that would increase the wavelength, which we don't want, so it's not going to be A. B is a nitrile group. Again, I won't draw all these out. Nitrile has this nitrogen bond, which we wouldn't want. An alkyl group, you'll know, is just something like this, or this. This is an alkyl group, and it's obviously not got any double bonds in it. It's got none of these conjugated bonds, and so that won't increase the wavelength. So C would be the answer here. But then just for completeness, let's talk about an aryl group. Of course, it has a double bond in it as well. So the answer for this one is definitely C. If we're looking at 83, then it says the structure of beta-carotene is shown, and we're asked what is the reason why beta-carotene is orange. So looking at the structure, we have got these 2 aromatic ends, but we've also got lots of conjugated bonds in the middle. So we're asked what the reason is for why it's orange. So if it's orange, that means it reflects sort of the red spectrum of light, and that means it absorbs the blue end of the visible spectrum. So that immediately rules out 2 of them. We're told about how it has to be an aromatic group, and we can see that there isn't these like benzene like structures because there's only one double bond present at the two ends in those rings that are present on the beta carotene. So that leaves us with these 11 conjugated bonds that separate the two. And if they're going to absorb the blue end of the visual spectrum, that means we're going to be left with the red part of the spectrum, making that particular compound orange. So that gives us an answer for 83 of C. Then finally, 84 says phenolphthalein is an acid-base indicator. It is different structures at different pH values. And we're given the two structures here, but I'm going to simplify it. We have sort of a base and a conjugate base here, or an acid and its conjugate base. So another way you can think of it is this is structure 1 and this is structure 2. And you can see how these sort of carboxyl groups would separate out like this. Now, obviously, this is a bit of an oversimplification, but if you think of it in these terms, it makes it a lot easier. Because the dissociated version of this particular, let's call it a weak acid, the dissociated version of this will be present at a higher pH. And at a low pH, we know that it will be colorless. And that means that 1 has to be the structure at a low pH, because this is the unconjugated form, and this is the dissociated form. So this will be present at a low pH, and this will be present at a high pH. And that straight away gives us our answer of A for 84. So that was questions 81 to 84.